We're now going to context switch from papers that focus on improving the RL training model to papers that improve the general ecosystem. Our next paper is going to be by Yihao Zhao from Peking University. His interests are systems and networking with a focus on large-scale scheduling problems. His advisors are Xinjin and Xuanzhi Liu. He'll be talking to us about a resource scheduling problem, or actually a multi-resource scheduling approach to improving deep learning training. And with that, I will hand it over to the video.
Hello, everyone. I'm Yihao from Peking University. Today, I'm glad to share our work, Multi-Resource Interleaving for Deep Learning Training. This is joint work with Yuanqiang, Xuanzhe, and Xin from Peking University, Yanghua and Yibo from ByteDance. In recent years, deep learning is becoming popular. A wide spectrum of deep learning models is proposed for various fields, such as computer vision, natural language processing, and reinforcement learning. Deep learning training has become an important workload in enterprises clusters. Deep learning training uses multiple resource types. The training process is iterative, that is to say, one iteration after one iteration. For each iteration, there are usually 4 stages, and each stage mainly uses a specific resource type, specifically storage I/O for loading training data, CPU for preprocessing and simulations, GPU for forward and backward propagation, and in the last, network I/O for communication in distributed training. Nowadays, deep learning models vary dramatically in model size and types, and training them is bottlenecked on different resource types. For example, training tiny deep learning models is usually bottlenecked on the storage I/O. Training IL models relies on CPUs for simulations, making CPUs the bottleneck. Besides, GPU and network I/O are the bottleneck of NLP jobs and distributed training jobs, respectively. To train deep learning models, enterprises build GPU clusters. The GPU cluster is composed of lots of nodes, and each node contains the aforementioned 4 resource types. Users submit deep learning training jobs to the cluster, and the scheduler schedules jobs and allocates resources. The goals of cluster scheduler are like minimizing the finish time of jobs and maximizing resource utilization. Existing efforts have made significant progress in deep learning scheduling. However, they assume that GPUs are the bottleneck in deep learning training. Most deep learning schedulers allocate GPUs to a job exclusively. Some explore resource sharing, but they consider only GPU sharing. As deep learning training is bottlenecked on different resource types, these schedulers made the opportunity of multi-resource sharing. There are 2 main challenges of multi-resource sharing. First, sharing resources may bring great interference and affect the training speed, especially for GPU. So we need to reduce interference among shared deep learning jobs. Second, considering the goal of the cluster scheduler, we need to improve both job and cluster efficiency. To solve the challenges, we propose Muri, which utilizes multi-resource interleaving to improve both job and cluster efficiency. There are mainly 2 techniques in Muri. The first one is multi-resource interleaving. Muri packs jobs to share the same set of resources by interleaving their stages in time. We can reduce interference among shared jobs with multi-resource interleaving. The second technique is the blossom-based scheduler. The scheduler decides the jobs in one sharing group and their sharing patterns to improve both job and cluster efficiency. Muri is composed of Muri scheduler and Muri executor. Users submit deep learning training jobs to the Muri scheduler. The Muri scheduler maintains a job queue to buffer the submitted jobs and makes job scheduling decisions. There are 3 components in the Muri scheduler. First, the resource profiler profiles the resource usage for each job when it is first submitted. The resource profiler also estimates the interleaving efficiency at the input of the scheduling algorithm. Second, the job scheduler periodically schedules the job from the job queue to the machine in the cluster. Next, the worker monitor collects the resource information of each machine and tracks the progress of each job. The Muri executor is located on each machine. The executor receives jobs and grouping strategies from the scheduler and execute the jobs according to the grouping strategy. There are mainly two kinds of multi-resource sharing: space sharing and time sharing. Here, we show an example to compare these two sharing types. For deep learning training jobs A, B, C, and D are shown in blocks in different colors. We show one iteration of these four jobs. When a job cannot fully utilize one resource type, it can share the resources with other jobs. When the jobs are shared in space, at every moment, each resource type on one machine is used by multiple jobs. As for time sharing, we can shift the stages of different jobs and share the resources among the jobs. At every moment, each resource type on one machine is used by only one job. In space sharing, due to the interference among shared jobs, each stage is lengthened. The iteration duration of space sharing 9 is much longer than the iteration duration of time sharing 4. Apparently, time sharing is the one that can solve the challenge of interference. And time sharing provides higher resource utilization and a lower cost for cluster provider. Muri utilizes the fine-grained multi-resource interleaving to share jobs in time. Two characteristics of deep learning training enable time sharing. First, each iteration of deep learning training has 4 stages in general, and we can shift the stages to perform multi-resource interleaving. Second, the iterative pattern of deep learning training enables us to make interleaving decisions at the job level, whose overhead is low. In practice, pipelining is commonly used to overlap the usage of different resources. For example, it is common to overlap the gradient synchronization with backward propagation, which overlap the GPU and network. We remark that pipelining exploits the intra-job aspect, while multi-resource interleaving exploits the inter-job aspect. Here, we show a simplified example to illustrate the benefit of multi-resource interleaving compared with pipelining. We show the resource usage of GPU and network I/O of two jobs A and B. GPU is underutilized for job A, and network is underutilized for job B. The throughput is calculated for the same set of resources. Interleaving jobs A and B as shown on the right can improve the throughput by 1.7 times in comparison with running them separately. To maximize resource utilization, we need a metric to compare different grouping plans. Here, we use interleaving efficiency to represent how perfect the grouping plan can overlap the resource usage of the jobs. Better resource interleaving efficiency means the less idle time of the resources. Therefore, we define the resource interleaving efficiency gamma as the fraction of time that some resources are occupied. To take into account all resource types, we take the average occupied time ratio of each resource. The iteration duration can be estimated by adding the maximum duration of concurrent stages of interleaved jobs as shown in the blue equation. Given some jobs, Muri scheduler groups these jobs so that the interleaving efficiency of the entire grouping plan is maximized for higher resource utilization, along with shorter job completion time. First, let's consider a simplified problem in which at most 2 jobs can be grouped. We can formulate this problem as a maximum weighted matching problem. Specifically, we build a graph where each node represents a job. For example, there are 4 jobs at the beginning, and every 2 jobs are connected by an edge with the interleaving efficiency of grouping these 2 jobs and the edge weight. Then, a grouping plan corresponds to a matching of the graph. Therefore, finding the optimal plan can be converted to finding the maximum weighted matching of the graph from all possible matchings. Maximum weighted matching is a well-studied problem in graph theory. Blossom algorithm can find the optimal matching in polynomial time complexity. However, the problem becomes complicated when the resources are more than 2 types. With k resource types, we need to consider matching k jobs on a k-dimensional hypergraph, where each hyperedge represents grouping k jobs. Finding the optimal grouping plan is transformed to maximum weighted k-uniform hypergraph matching in graph theory. And this problem is NP hard. We design a multi-round heuristic algorithm to handle multiple resource types. The main idea is to divide the matching process into multiple rounds, and each round uses Blossom algorithm to group jobs. At the end of each round, each pair of nodes in the selected matching is merged into one node. The heuristic algorithm still has an acceptable polynomial time complexity. We also optimize Muri from other aspects. First, in widely used distributed training, workers require intra-job synchronization. For example, job A on GPU 2 has to synchronize with that on GPU 1. On the other hand, multi-resource interleaving introduces new dependencies between jobs. In this scenario, interjob interleaving interacts with intra-job synchronization, which brings additional slowdown for job C. To avoid the slowdown, Muri only grouped jobs with the same GPU requirements. Second, given multiple resources, there are several orderings to interleave the jobs, and different orderings have different interleaving efficiency. To address this problem, we enumerate all the orderings to find the best one. Additionally, as multi-resource interleaving reduces mixspan inherently, we optimize for the other common metric, average GCT. Muri assigns a priority to each job according to two effective methods, SRSF and 2DLAS, to minimize average GCT. With this design, we implemented a prototype of Muri with about 7,000 lines of code and integrated it with PyTorch. Our evaluation is performed on a 64 GPU cluster using NVIDIA V100 GPU. We use the real-world traces from Microsoft and its mixed popular deep learning models. We evaluate the overall performance of Muri using 400 deep learning jobs submitted over 10 days. Our evaluation covers both scenarios when the job durations are known and unknown. The metrics are normalized with those of Muri. Compared with baselines, Muri achieves higher job efficiency. Whether the job durations are known or unknown, Muri improves average GCT by more than 2 times and improves tail GCT by more than 2.5 times. Additionally, Muri achieves higher cluster efficiency with more than 1.4 times faster mixspan. To show the benefits of Muri in detail, we evaluate some detailed metrics. These figures show the GPU and CPU utilization of baselines when the job durations are unknown. The yellow line shows the resource utilization of Muri. Muri achieves 36% higher GPU utilization and 30% higher CPU utilization on average, demonstrating that Muri is capable of utilizing idle resources by interleaving stages of different jobs. For more detailed metrics, please refer to our paper. We also conduct trace-driven simulations to evaluate Muri with a variety of workloads. Here, we perform simulations over 4 traces, with job numbers varying from about 1,000 to 6,000. In simulations, we compare Muri with one more baseline, Ant-Man, which is the state-of-the-art GPU sharing scheduler. As shown in the figures, Muri improves average GCT, mixspan, and tail GCT greatly. Our paper has many more experiments, including the performance when job durations are known, more detailed metrics, and analysis of Muri. To conclude, Muri is a multi-resource cluster scheduler for deep learning workloads. It introduces multi-resource interleaving to share jobs in the time dimension, and utilizes a Blossom-based scheduling algorithm to maximize the interleaving efficiency. By doing so, it improves both job and cluster efficiency, reflected by average GCT and mixspan, respectively. Muri is open sourced at the listed URL, and thank you for listening.
We have time for a few.
Thank you. have a good voice, so I can...
There's another mic over there.
Thank you for your talk. So first, it's great to see that a concept like from pipe dreams and other pipelines, parallel pipelines are being taken for other industries. But my main concern, and I wanted to know if you did anything about that, is about security. Since you're now interleaving between processes that belong to two different jobs or two different customers, for example, we know that today, for example, if you want to share a CPU, usually in order to, when you move to a different process, you do TLB flushes in order to prevent issues like Spectre and Meltdown. So have you, when you tested your environment, have you did all cleanups between movement, between process and process in order to see the performance increasement, or you just did a sharing, like a straightforward sharing, without any cleanup on your system?
Okay, thanks for your question. And it's true that the security is an important problem if we want to deploy it in a large-scale clusters. As for now, in Muri, we merge the shared jobs into one process and into one CUDA context to schedule and interleave. And besides, in Muri, we also use work monitor to monitor the training process. And once error happens, the monitor will ask the executor to execute the shared jobs again. And I believe that enhancing the security and some experiment to show whether it's secure enough among the shared jobs is an interesting direction to explore in the future. Thank you.
Thank you.
Hi, thanks for the talk. So I wonder, maybe I missed this part, but how do you actually measure the resource requirements for different jobs, or you just assume everything is already known?
Okay, thanks for the question. And there's a component in our Muri scheduler called resource profiler, and we use PyTorch profiler or other profiling tools to profile the resource usage of the submitted jobs. And as the resource usage is relatively stable between the executions, so we can store the profiling results in a database, but only profile the usage when the job is first submitted.
Okay, thanks.
Thank you.
Let's thank our speaker once again.
Thank you.